So now we're going to show that the expected preprocessing time as well as the expected size of the data structure is as we claimed. So I'm going to claim first that the expected size can be bounded using this equality, where Ki is the number of trapezoids created when inserting Si. To see this, let me go back a few slides and look at this picture. Okay. So here, when I have this structure before inserting Si, the Si segment intersects a bunch of trapezoids. So in this case, trapezoids C, D, and E, and therefore the leaf nodes C, D, and E are turned into internal node that store Si, and then I add additional leaves here. What we can observe here, the running time as well as the expected growth in the space is all bounded by K, which is also asymptotically bounded by the number of new leaves created. Okay, so if I want to bound how much asymptotic work as well as how much asymptotic growth in the space is, it can be simply bounded by the number of new leaves created after inserting Si. So let's go back. So here I want to bound asymptotically. So again, I've ignored the O notation here. I want to bound asymptotically the size of the data structure. So we could see that this is bounded by this equality. And here again, I have switched the order of expectation and summation, because technically it is the expected value of the sum of Ki's, but you can switch them around. So therefore, I just need to bound the sum of the expected values. So I just need to find the expected value of Ki, the number of trapezoids created when inserting Si. We're going to use again backwards analysis. Assume that the segments I+1 up to n are already chosen in my random permutation. So now I have a fixed set of segments 1 to I. Okay. The claim is that the expected value of Ki is this slightly complicated looking formula. Let's go over it. Okay. So I have a fixed set of segments left, 1 to Si, which create a fixed trapezoid decomposition. So I have a fixed trapezoid decomposition here, whatever. So this is the trapezoid decomposition Ti. And I'm trying to figure out what is this expected value. I have I choices for my segment to be placed at the position I. Okay. Each one of them will be chosen at position I with probability 1 over I. Okay, so this is the probability, because I'm going by the definition of the expected value. The expected value of a random variable is the summation over the probability of a particular outcome times the value of the particular outcome. Okay, so this is the probability of choosing S as the segment number I. And I claim that this is essentially counting Ki. So this is basically Ki. The number of, sorry, not that one. Oops. This one. Okay. So this is, I claim this is Ki. The number of trapezoids removed from Ti when deleting Si. So let's go through the definition to see why this holds. So this delta is defined to be a 0, 1 value. So when I'm looking at a particular trapezoid in my picture, so for example, let's look at, I don't know, this trapezoid. Let's erase these things. So let's look at a particular trapezoid. Again, it's a this trapezoid delta. The probability that, so if this delta is removed when I'm deleting S, then this value is 0. As 1, but if it stays, then it's 0. Okay, so for every trapezoid, I assign a 0, 1 value. If it doesn't disappear, it's 0. If it disappears, then 1. So obviously, the sum of these 1s will be the total number of trapezoids removed when I delete S. Okay, so therefore, this equality holds. This is the probability of choosing S, and this is Ki, is the number of trapezoids removed when I'm deleting the particular value of S. And then, of course, I have the sum over all possible choices that I have for the last trapezoid, for the last line segment to be placed at position I. Okay, so this holds. So now let's move on to bound this inner term over here. So now let's look at this double summation to see what it counts. What this counts is that I count for every segment how many trapezoids are adjacent to that segment. In other words, this summation counts the number of segment trapezoid adjacencies. Right, so this is a number of trapezoid segment adjacencies. But there is another way to count the same thing, and that is for every trapezoid, I could count how many segments are adjacent to it, because that would also count the number of segment trapezoid adjacencies. For every trapezoid delta, I have at most 4 segments adjacent to it. So therefore, the number of segments that are adjacent to trapezoid is at most 4 times the size of the trapezoid decomposition. So therefore, I could bound this summation, this double summation, as 4 times Ti, and based on what we've already proved, this is O of I. Okay, and now once I plug this O of I inside over here, 1 over I cancels with I, so I get constant. So therefore, the expected increase in the size of the data structure is constant. So therefore, in total, that would take linear time. The expected pre-processing time is exactly similar, also not exactly similar, it's extremely similar to this. The expected pre-processing time at the ith step is essentially constant plus the time it takes to insert Si. Based on what we've chosen, this is log I plus the expected value of Ki. Why do I this log here? Well, this is because I need to do 1 point location. So go back. How do I find a trapezoid intersected by Si? Based on what we've covered, you find, let's say, this point. Let's say you find a trapezoid C by doing point location. But that takes log I time, because I have I segments, or on expectation that takes log I time based on what I've proven already, because I have I segments in my data structure. And the rest of the steps takes O of Ki time. So basically, if I go forward again, when it comes to pre-processing time, the time to take, this is just to find the segment, the trapezoid containing the left endpoint of the segment, and the rest is essentially O of Ki. And based on what we have proven earlier, this is the expected value of this is 1, and so essentially I just pay log n, and this is worst case log n, so this is n log n in the worst case. And that essentially proves what we wanted to prove for this data structure. The expected space is n, query time is expected log n, and pre-processing time expected